Okay, today we're going to be learning about how to solve linear first-order differential equations. So first, a reminder of what those are. So any differential equation that can be rewritten in the form dy dt plus some function of t times y equals some function of t is going to be linear. Notice that the derivative of the function and the function itself just show up on their own. The only thing that we're possibly doing to them is multiplying them by a function of t. It's also first order. The only derivative we see here is the first derivative. Okay, this format is called this way of writing the differential equation is called the standard form. We're going to have standard ways of writing differential equations that have like different types of differential equations. This is the standard form for linear first order DEs. I want you to notice a couple of things. The coefficient of dy dt is equal to 1. And the second thing is that y and its derivatives are on the same side. When its derivative, dy dt, are on the same side. Okay. All right. So we're going to be focusing on differential equations. We're almost always going to start by writing them into this standard form. Okay, so just to practice this definition a little bit, I want you to take a moment, pause the video, and look at the following 3 examples. What I want you to try and do is rewrite them if you can. Decide which of these are linear, which of these are nonlinear. So that means just not linear. Any one that is linear, I'd like you to write in the standard form. Okay. So you're welcome to do things like move things from one side to the other. You're welcome to do division as long as you maintain equality. So take a minute, look over this, and then unpause. All right, so when we're looking at this first one, notice that we see dy dt and y only show up as they are. We're not squaring them, we're not sticking them inside of any functions. So this is going to be a linear example. And we can rewrite it as dy dt minus ty equals 0. We're just subtracting ty over to the left-hand side. Just trying to match the format a little bit. Here we see p of t, the coefficient of the y function here, is going to be equal to negative t. And we see that g of t, the right-hand side, is equal to 0. And this guy is called homogeneous. Okay, if our right-hand side is 0, we'll give it this name, homogeneous. Okay. All right. Next, we look at the second example here. We see the derivative and the original function just show up as they are. They're allowed to have coefficients that are functions of t. So this is also linear. Okay, let's do a little bit of rewriting. I'm going to start by moving everything that like y and its derivatives to the same side. So that gives us t squared dy dt minus y equals t. Okay, so this is a first step towards being in the standard form, but we're not there yet because the coefficient function of dy dt is supposed to be equal to 1. So what we're going to do is just divide both sides through by t squared, or you can think of this as multiplying through by t squared. Make sure that the entire left-hand side gets divided through by t squared, as well as the entire right-hand side. Okay, so this gives us dy dt minus y over t squared equals 1 over t. I'm just going to write down what our coefficient functions are here. The coefficient of y, p of t, is equal to negative 1 over t squared. And our right-hand side, g of t, is equal to 1 over t. We're going to call this guy non-homogeneous, since we have a function that's not 0 on the right-hand side. Okay. All right, one last one to look at. We have t dy dt minus y squared equals 4. All right, and when we examine this, notice here we've got a y squared. Uh-oh, this thing is not linear. Okay, to be linear, we need that the function y and its derivatives show up as they are, no powers, not stuck inside of any other functions. Okay. All righty. Great.